The chain rule. The chain rule. I cannot even begin to stress how important the chain rule is to the subject of calculus. So far we've learned the power rule and the product rule and the quotient rule, which are all very important. But the chain rule allows us to take the derivative of a whole new class of functions, the composition of functions. And so many functions we deal with are going to be compositions of functions. But more than that, it's at this time I want to stress how important it is to be able to take the derivative of any function really. And even though right now we're talking about differential calculus and pretty soon we'll talk about integral calculus, they're not disjoint topics. It's really important that we understand how to find derivatives and how the rules really work, because in integral calculus we're going to basically undo those rules. So they really go hand in hand, and it's the fact that calculus is this building subject where you really had to know what happened before to be able to move forward that makes the subject so difficult. So, at this time I really want you to focus on understanding the differences in the types of functions, whether it is a product or a quotient or a composition of functions, and really commit right now, if you haven't already, to understanding the concepts in this subject. So with that said, let's go over the chain rule. Alright, the chain rule says that if f and g are differentiable functions, then the composite function f of g of x, which is also represented by f of g of x in this notation, is also differentiable, and its derivative, so the derivative of f of g of x, is equal to f prime of g of x times g prime of x. So this is a pretty tricky rule to try to understand the way that it's written. So here's how I like to think about it. So here's what we're trying to do. We're trying to take the derivative. We're trying to take d dx of f of g of x. So let's write g of x in a different color. So g of x is inside of f of x. So g of x is going to be my inside function here, and f of x is my outside function. Alright, so then what the chain rule is saying is that what I'm going to do is take the derivative of the outside, leaving the inside the same. So the derivative of the outside of the inside. So here's where I want to be really careful with how I wrote this, is that this is not multiplication. This is of. So the derivative of the outside of the inside, so we leave the inside the same, and this is multiplication. So times the derivative of the inside. So down here I wrote it in words. The chain rule says to take the derivative of the outside function while leaving the inside function the same, then multiply by the derivative of the inside. So take the derivative of the outside while leaving the inside the same, then multiply by the derivative of the inside. So try to keep that in mind. Have this in your notes so we can go through the next couple of examples where at first we're just going to identify which one's the inside function and which one is the outside function. Alright, so identifying the outside and the inside functions. So here we have sine of x squared. So what I'm going to do is I'm going to create two columns, one for outside functions and one for inside functions for each of these problems. Alright, so the inside function we're going to work on first. Right now, x squared is inside the function sine x. So what that means is that we're going to take x squared and substitute it into the x value to get sine of x squared. So inside in our formula is g of x, and outside is f of x. So let's keep going. Here I have sine of x as a quantity squared. So here's where it's important to understand that this is the same as sine of x in parentheses squared. Because now it's clear that, or hopefully it's clear, that sine x is on the inside. So sine x is being raised to the second power. So my inside function is sine x, and sine x is being plugged into x squared. So it's like I'm substituting in this inside column into the x of the outside column. So now let's take a look at the next one. I have the square root of 2x minus 1. So 2x minus 1 is inside of a square root. So 2x minus 1 is the inside function, and it's inside of the square root function, the square root of x. So let's keep going. Here I have the cube root of cosine x. So cosine x is inside of a cube root. So cosine x is the inside function, and the cube root of x is the outside function. Alright, so here I have 1 over x squared minus 1. And you might be thinking, I don't see any inside and outside. I see a numerator and I see a denominator. And I agree with you. There is a numerator and there is the denominator, and you could absolutely use the quotient rule. However, the 1 in the numerator tells me that I might think of doing some simplifying first. So x squared minus 1 in the denominator is a quantity, and that quantity is being raised to the first power. So what I can do is I can rewrite this by bringing the entire quantity to the numerator, x squared minus 1, and changing the exponent to the opposite sign. So this is the same as x squared minus 1 to the negative 1. Now, hopefully at this point you see that the inside function is x squared minus 1, and what I'm plugging it into, the outside function, is x to the negative 1. So I'm plugging x squared minus 1 into this x and raising it to the negative 1 power. So now let's continue to look at some more problems. I have 2x plus 3 as a quantity raised to the 7th power, so my inside function is 2x plus 3. And this whole quantity is being raised to the 7th power, so what I'm doing is I'm taking 2x plus 3 and plugging it into x to the 7th. And then this last one's a little different. I have e to the x squared. So in this case, x squared is the inside function, because x squared is being substituted into the x of the exponential function e to the x. So that would make e to the x the outside function. So the biggest part of the chain rule is identifying when you have a composition of functions, or in one of the previous cases, in this one, recognizing when you can turn a function into a composition of functions to help work in your favor and apply the chain rule. Because once you've mastered the chain rule, it's going to make taking so many derivatives much easier. And some of them can only be solved using the chain rule. So now that we have gotten some practice identifying the inside and the outside function, let's try to apply the chain rule to find derivatives. Alright, so let's take the derivatives of the functions where we just identified the outside and the inside. So what I did was I wrote out in words how I like to think of the chain rule. So the chain rule says outside prime of inside times inside prime. So we want to take the derivative with respect to x of sine of x squared. So what we need to do is take the derivative of the outside function. So the outside function here was sine x. So the derivative of sine x is cosine x. But here's where I want to be really careful. It's outside prime of inside. Right now, this is cosine of x. The inside function is x squared. So in other words, instead of taking the derivative of sine x and saying that the derivative is cosine x, it has to be the derivative of the outside, and we leave the inside part the same. So this part here is the derivative of the outside function while leaving the inside part the same. So cosine x squared, and then we have to multiply by times the derivative of the inside prime. So the derivative of x squared is 2x. So typically we write the 2x in the front so that this derivative would be 2x cosine of x squared. Now, the biggest mistake is that students think that the outside function is sine x, so they need to put cosine x. So they'll sneak in a little extra x right here and right here. And that is not correct, and that's why this is probably the most important word. Outside prime of inside. and then times inside prime. So I don't want to sneak that extra x in there that doesn't actually belong there. So that should not be there. So the final answer is 2x times cosine of x squared. So now let's try the next example. So here I have the derivative with respect to x of sine of x as a quantity squared. So I'm going to rewrite it. So this is sine x as a quantity squared. Alright, so the outside function here is x squared. So let's remember that in the back of our mind. The outside function is x squared. And the derivative, so remember the formula says the derivative of the outside function, the derivative of x squared is 2x. But remember, we want to leave the inside the same. So we're going to go ahead and put 2, but instead of x, the inside is going to be sine x. So instead of x, I'm going to replace this with sine x. So 2 sine x times the derivative of the inside now. The derivative of sine x is cosine x. So we took the derivative of the outside function. So the derivative of x squared is 2x. So it's like we brought the 2 to the front and left the inside the same, and then multiplied by the derivative of the inside. So 2 sine x cosine x is the derivative of sine x squared. So now let's go ahead and take a look at the third example. The inside function we decided was 2x minus 1, and the outside function was the square root of x. But instead of thinking about it as the square root of x, what I'm going to do is rewrite this as 2x to the 1, or 2x minus 1 to the power of 1/2. So the outside function here is like x to the 1/2. So we can write that for a note for ourselves. The outside function is like x to the 1/2, and the derivative of x to the 1/2 is 1/2 x to the negative 1/2. But again, instead of this x, I'm going to leave the inside function. So this is 1/2 2x minus 1 to the negative 1/2 times the derivative of the inside function, which would just be 2. So now everything's being multiplied. This 1/2 and this 2 cancel. So it's 2x minus 1 to the negative 1/2. Well, if I don't want negative exponents, this is 1 over 2x minus 1 to the 1/2, or 1 over the square root of 2x minus 1. And if you really don't want radicals on the bottom, then we can multiply here to rationalize the denominator. But for now, we're just going to go ahead and leave our answer like this. This is fine. So let's keep going. I want to take the derivative with respect to x of the cube root of cosine x. So I'm going to rewrite this as the derivative of cosine x to the power of 1 over 3, so that I can see that the outside function is again x to the 1/3. So the derivative is 1/3 x to the negative 2/3. So again, instead of x right here, I'm going to replace that with this inside portion. So it's going to become 1/3 cosine x to the negative 2/3 times the derivative of the inside. The derivative of cosine is negative sine x. Now I want to stop right here and point one thing out, that I have to put parentheses right here, because if not, if I go ahead and just write times negative sine x, that's going to look like a minus sine x, right? And it's times negative sine x. And when we continue to simplify this, we write this as negative 1/3 sine x cosine x as a quantity to the negative 2/3, or I can leave the sine x in the numerator, and then put the 3 in the denominator and turn this into cosine x to the positive 2/3. So I could do that as well. Alright, so moving on, trying some more examples. For this problem, again, I could use the quotient rule if I wanted to, but we're trying to practice how and when we should probably use the chain rule. So here, I can rewrite this as x squared minus 1 to the negative 1. And so now, I'm going to try to not write the outside function. What I'm going to try to do is recognize the outside function is x to the negative 1. So what this has amounted to is it has amounted to taking the exponent and bringing it to the front, so negative 1, and then leaving the inside the same, x squared minus 1, reducing the power by 1, times negative, or to the negative 2, times the derivative of the inside, which would be 2x. So this becomes, simplified, negative 2x over, I'm going to move this to the denominator and make the exponent positive. So x squared minus 1 squared. So this is going to be the derivative of this original function. And maybe you can see a little bit how the quotient rule would give you the same answer, right? Low d high minus high d low over low squared. So x squared minus 1 squared would give you the same answer, but this was a lot less work to do. So we just had to recognize how to rewrite it, and then it was really like a two-step problem to get to the most simplified answer, as opposed to low d high minus high d low over low squared and then simplifying would have taken quite a few more steps than these two direct steps here. And so now, let's take a look at the next one. So 2x plus 3 to the 7th. What I want to point out is that if we really wanted to, we could distribute here. But what that would mean is multiplying 2x plus 3 times 2x plus 3 times 2x plus 3 7 times. And then, doing all that distribution, and then using the power rule. So while it's possible to do this without the chain rule, it is not advised. So the chain rule says take the derivative of the outside function. So the outside being x to the 7th. So we're going to bring the 7 to the front, leave the inside the same, 2x plus 3, reduce the power by 1, and then multiply by the derivative on the inside. So the derivative of 2x plus 3 is 2. So 2 times 7 gives me 14. 2x plus 3 to the 6th. So notice how much less work we had to do to find the derivative, as opposed to having to do all of that distributing just to get a polynomial that we can finally take the derivative of using the power rule. So this here is my answer. That's it. And not only that, just real quick, there was no way we were going to get this simplified of an answer too. If we were to distribute everything out and use the power rule, we'd get this really long, ugly, messy answer, when really it's just this nice little function. And then here we have the derivative with respect to x of e to the f of x. So f of x is inside e to the x. So the derivative of e to the x is e to the x. But remember, we don't want to write e to the x, we want to leave the inside f of x alone. So it's e to the f of x times the derivative of the inside, and the derivative of f of x is f prime of x. So now I want to use this generic example to help me solve this next problem. So we agreed x squared is inside of e to the x. So notice what we did here. I had e to the f of x, and the derivative was just repeating e to the f of x, and then multiplying by the derivative in the exponent. So the same thing is going to happen here. We're going to have e to the x squared, so the derivative of e to the x is e to the x, but we leave the inside the same, so we leave it as e to the x squared, times the derivative of the exponent, or the function in the exponent. So the derivative of x squared is 2x. So to simplify this, we're going to have 2x e to the x squared. And then to look at just a few more examples of when we have generic functions. So here I have the derivative with respect to x of f of x as a quantity raised to the 7th power. So the outer function is x to the 7th. So the power rule is going to give us 7x to the 6th, but instead of x, we leave the inside the same. So 7 times f of x raised to the 6th power times the derivative of the inside, which is f prime of x. And there's no simplifying here that I can do. I would just leave it like this. Now this next one's a little bit different. So the derivative with respect to x of f of 7x. So now 7x is the inside function. So the chain rule says take the derivative of the outside. So the derivative of f is f prime. And we leave the inside the same. So the inside is 7x. So f prime of 7x times the derivative of the inside. Now the derivative of 7x is 7. So the only thing we can really do with this is bring the 7 to the front and say 7f prime of 7x is the derivative. And then finally we have the derivative with respect to x of sine of f of x. So the derivative, the outside function here is sine x, the inside is f of x. So the derivative of the outside is cosine x, but we don't put x, we put the inside function, so cosine f of x, times the derivative of the inside. So the derivative of f of x is f prime of x. So this is the final answer. There's nothing that we can do with this. So the derivative of the outside, leave the inside the same, times the derivative of the inside. Alright, so while it's impossible for me to go over every type of example, I have two more that now combine rules. So the derivative with respect to x of sine of e to the x times x squared. So we have a product inside of a composition of functions. So first let me clarify that what I cannot do is I cannot use the product rule right now at the start on the inside of this function. I have to start by using the chain rule, because then we'd be assuming that we can just take the derivative of the inside and then do the derivative of the outside, which is not the case. That's not the chain rule. So the chain rule says we take the derivative of the outside function, derivative of sine is cosine, and we leave the inside the same. So e to the x times x squared. And then we multiply by the derivative of the inside. So now here is when we're going to use the product rule, because the inside is a product. So the product rule says the first function, e to the x, times the derivative of the second, so derivative of x squared is 2x, plus the second function, x squared, times the derivative of the first, the derivative of e to the x is e to the x. So now I would go ahead and advise that you leave your answer just like this. There's not really a whole lot we could do with it. If we really want to, let's see, cosine e to the x, x squared, we can factor out an e to the x from this expression. So e to the x times 2x, well actually we could factor out an x e to the x, just not sure how much nicer this looks, and we're left with a 2 plus x. So we can pull out an x e to the x and we're left with 2 plus x. So technically this is the most simplified answer. So it's worth going over it. And now the final example of where we're combining more than one rule is using a quotient rule and a chain rule. So here we have the derivative with respect to x of cosine squared x over e to the x. So what I'm going to do first is rewrite this. The numerator is cosine x as a quantity squared over e to the x. So in the numerator, there's a chain rule. But I cannot just take the derivative of the numerator right now and apply the chain rule. I would have to apply the quotient rule first. So within the quotient rule, when I get to taking the derivative of the numerator, then I'm going to apply the chain rule. So right now, it's the quotient rule. So low d high, e to the x. Now, d high, the derivative of the high function. This is when I'm going to have to use the chain rule. So the outside function is x squared. I'm going to bring the 2 to the front. So the derivative of x squared is 2x, but instead of x, I'm going to put cosine x. Reduce the power by 1, so it would be 2 cosine x to the 1, times the derivative of the inside. The derivative of cosine x is negative sine x. So what have I done so far? Low d high minus high So I'm going to write that as cosine squared x d low. The derivative of e to the x is e to the x all over low squared. So e to the x squared. So now, let's see, on this left-hand side, what can I do? I can write negative 2 e to the x sine x cosine x. So everything on that left is being multiplied. I just pulled the negative and the 2 in the front. And then minus e to the x cosine squared x all over. E to the x squared is the same as e to the 2x. And now I can, let's see, I can factor out of the numerator a e to the x and a cosine x and a negative. So let's pull out negative e to the x cosine x. And what I'd have left is 2 sine x plus, because I pulled out a negative, cosine x all over e to the 2x. But what I'm going to do is write that as e to the x, because now an e to the x will cancel because they're being multiplied. We'll make ourselves a little bit more space so that the final answer is negative cosine x times 2 sine x plus cosine x all over e to the x. Alright, the last thing I want to show you is a funny pie chart that I found online that could not be more accurate. So I have taught calculus now for a few years here at Alma, but I also taught at UC Riverside, and I have to tell you that this is absolutely true. The sources of error in calculus, mostly arithmetic and algebra, is where most of your mistakes are going to come from. So in that simplifying stage, it's really going back to basics and understanding the properties of when and how you can cancel and distribute, multiplying, dividing, common denominators, those types of things are the biggest errors in calculus. Right after that, the chain rule, which is what we covered today. So the chain rule is right up there with a lot of the mistakes students make in calculus, followed by integration, which we haven't gotten to yet. But it's funny, but it's not, because they are easily avoidable mistakes with practice. So if you practice your arithmetic and your algebra, you don't just settle for getting the answer and leaving it in your homework. You keep going all the way and get to that reduced answer that matches the one in the back of the book, and truly understand how you got there, then your algebra mistakes will disappear. And then the chain rule is just practice, practice, practice. So I tried to go over as many examples as I could so that it can help you, but ultimately there's just too many different types of examples to go over. So you're going to have to get that practice through your exercises, and should you ever need them, I have tons and tons of chain rule practice worksheets.